a coordinate system yesterday, a kind of coordinate, okay, which describes the, so let me write that. So this was the coordinate we defined yesterday. Okay, so this is the following coordinate. This is null coordinate. These things we have already done yesterday, and we have figured out dp by dr is equal to 0 implies is p equal to constant. So this is for what? Ingoing photon, and we are having dp by dr 1 minus twice mu by r raised power of minus 1 plus p is equal to 2r plus 4 mu dash r by twice mu minus 1 plus some constant of d. So this was outgoing photon. So this is what we have done, and we have figured out the light cone structure yesterday. Okay, there is actually this r equal to 2 mu line. Okay, so that acts as a membrane. In a sense, you pass from outside to the inside, and you are not able to move from inside to outside, is it? So there is a one-way traffic across that very boundary. Samajh that we have seen yesterday. Okay, so let me introduce. So instead of working with, okay, so let me draw a diagram. Instead of drawing a diagram, before that, what we will do, we'll introduce actually. Okay, so so this point, let me put it this way. So our Schwarzschild coordinates y. So you are having Schwarzschild coordinates. This t, r, theta, phi. Clear? Now, when I introduced this very coordinate system, what I removed? We removed t, is it? Okay, so we had this very coordinate system. Then we moved to p, r, theta, phi. Yesterday we have seen it. Clear? So this kind of coordinate system, we call this as usually. Okay, so it is known as advanced Eddington-Finkelstein coordinate system. Okay, so much more. So instead of using this parameter t in this very coordinate system, I'll introduce an equivalent quantity of this t. So much more. I will put it in the value of t. Okay, so what I mean by that? So let me introduce a time-like coordinate. Since this p, okay, so p is actually a null coordinate because it's a null geodesic. It specifies the null geodesic. It's actually a null coordinate. Okay, because if you see, p specifies both incoming and outgoing photon. Clear? And the photon moves along a null geodesic. That's why it's a null coordinate. What I will do, I will introduce actually a time-like coordinate instead of these null coordinates. Samajh? So let's try it. Let's introduce a time-like coordinate in terms of this p actually. Let's call that as t prime. Okay, this t prime is actually a coordinate, a time-like coordinate in which coordinate system? Eddington-Finkelstein coordinate system. Okay, and this t is a time-like coordinate in Schwarzschild coordinates. Got it? Okay, so how I write it? So let me introduce it, define it this way. So this coordinate, this time-like coordinate, I will write it as p minus r. So what is our p? Okay, so let's write. So what it will be? So it is simply pct, okay, plus twice mu natural log of r by twice mu minus 1. So what is our new coordinate system now? Just tell me. So our new coordinate system is this thing. Okay. T prime r theta and phi. So now let's look at, okay, so let's look the metric in this very coordinate system. Samajh? So what I need to do, so what was the metric in the previous coordinate system? In this p r theta, what was the line element? What was the line element? Yesterday we have done it. So I'm just repeating. Okay, so in this P R theta phi, so what was our this line element? It is ds square minus 1 minus twice mu by r. Okay, dp square plus twice dp dr plus r square d omega square. Clear? So now let's calculate. Okay, so let's calculate instead. Okay, let's remove this p from here, this dp square from that very equation. Okay, so this equation gives you, just tell me. So let's calculate it. So it implies c dt prime is equal to dp plus dr. Clear? Sorry, minus. So what it gives me, c dt prime plus dr, okay, square is equal to dp square. So you can now calculate all the terms. So just calculate this dp square. dp you know, so you use the value of dp. So this is dr, okay, this okay, dr you know, okay, you know the dr in terms of this. Sorry, you know dp in terms of this dt prime and dr, and you know now dp square. So what it gives me, okay, so my line element becomes like this thing, minus 1 minus twice mu by r. This will remain as said, c square dt prime square plus 4 mu c by r dt prime dr. Okay, minus 1 plus twice mu by r dr square plus r square d omega square. If you see whatsoever coordinate change we have done, it does not affect, change this theta and phi. Clear? So it remains always the same. So that you are only doing the coordinate transformation for the radial coordinates. So you are only, the coordinate transformations are only affecting what? X and t, you can say, r and t plane. It does not affect the theta and phi plane. You got my point. So that, okay, so that means whenever you try to write any kind of coordinate system or any kind of, let's say this line element, you can ignore this for the time being. At the end of the calculation you can put it back, because this does not get affected. So samajh aa? Everybody followed it? So everybody followed it, how it comes. So if you are not able to do it, just look here. So dp square is what? C square. So what you get? C square dt prime square plus dr square plus twice c dt prime dr. Okay. So now use this dp square here. Okay. Then you are having dp from here. Okay. So from here you are having dp how much? C dt prime plus dr. Use this thing and rearrange the terms. Simply. Clear? Okay, good. So now what is our, okay, so forget about this thing. What is our null geodesic? Okay, so let's, in this very new coordinate system, we need to figure out the null geodesic, because once we know the null geodesic, what we will do? We are able to figure out the light cone structure, is it? Null geodesic simply gives you the light cone structure in this very space-time. Now there, okay, if you remember, when we start with the Schwarzschild metric or this line element, you go from t to minus t, it was invariant, is it? Because there was no cross term. Now you are having a cross term between r and t, is it? So when you take t prime to minus t prime, it is not invariant kind of thing. Samajh Shaman? Clear? So this is a very important point in a sense. That means we can not construct the t equal to minus t domain from the same metric. So you are only in the one domain of your space-time. So you are, let's say, if you are having a regions which are connected by t and minus t, okay, that kind of symmetry that is broken here. So that's why we call them as the advanced kind of thing. There will be, in a moment, we will introduce another kind of coordinate system which we call the retarded kind of thing. You will see something different is happening. Okay, that's simply a mathematical curiosity. Huh? Okay, everybody is following it. Okay, so what is our, now tell me what will be the null geodesic? What is it? So let's look at the incoming and outgoing these photons. Okay, so incoming and okay, so what is our incoming photon line geodesic? Can anyone tell me? Now look at this very formula. You are in terms of, we are now figuring out in terms of T prime and R. What is for incoming line, incoming photon? P is constant, is it? So what it will be? So Ct prime is equal to minus R plus constant. So from this very equation, look at this very equation. Okay, because for incoming photon, P is a constant. Now let's look at for the outgoing photon. This we have already done from the diagram yesterday. So what is for the outgoing photon? So P has some value. You remember?
Yes, sir.
Okay. So let me write that. So it is Ct prime is equal to, so it will be R plus 4 mu natural log of R by 2 mu minus 1. Okay. Plus some constant again. Because this P contains constant as well. Some constant. Okay. Some integration constant. Okay. Now look here. Now we have extended, look, Schwarzschild coordinates were applicable only between RS and RS to infinity, is it? The Schwarzschild radius to the infinity. Okay. So let me write it. Okay. So you are having Schwarzschild coordinates. So here R was actually limited by this 2 mu or RS. So this RS is actually 2, the Schwarzschild radius, okay, in Schwarzschild coordinate, and T go from minus infinity to plus infinity. Okay, now let's look at these Finkelstein coordinates. What happens to T? Now R is going from where? Now in this very coordinate system, R goes to 0 as well, because we have seen yesterday the ingoing line of the photon, or the ingoing trajectory of the photon moves across the RS. That's a continuous line. Okay. So here R goes from infinity to 0. So that means we have covered this very region. Clear? Okay. So now let's draw the diagram. What we have drawn yesterday. Okay. So you are having this as a singularity line. So this is your R. Now we are in the Ct prime coordinate system. Okay. So let's call this as R equal to 2s. Now tell me what was the light cone in for this very coordinate system. So at infinity you are having what? Just tell me. So it was at 45 degree. Let me again write, and this was on. This is the ingoing line and this is the outgoing line. Okay. So this was at 45 degree. Okay, because we are at the infinity. Clear? Minkowski space applies. Okay, but this is a constant line, ingoing line. It will be like this thing. Samajh? So now tell me, why will be the trajectory of a massive particle? Let's say some particle is carrying mass, is moving. So that will be actually in the forward light cone. Samajh? You got my point? So what will be the direction of the line? So it will be actually in this very direction. Within this very domain, it will be in this very direction anywhere. Clear? So now let me move a little bit. So what will happen to this light cone? It will shrink. What happens here? So the slope becomes infinite. And this ingoing line remains as such. Now tell me, let's draw now the trajectory. Okay, so let me write it like this thing. Okay, so because this will shrink towards when it reaches R equal to 0, so they will close up. Everybody is following? This we have done yesterday.
Yes, sir.
Okay, so everybody is getting it. Okay, now tell me, what should be the line for a massive particle? It should be like this thing. Okay, so let's draw it. for an ingoing particle. So a particle is moving, so it will be like this thing. So it will be actually a continuous line. So in a moment I will draw. So let me write some trajectory. So it will be something continuous line, because as it passes, it crosses actually r equal to 2s. So what will happen here? So it again crosses what? So these are actually the continuous lines. So let me draw them in a good fashion. Okay. So what are the incoming and the outgoing lines? Okay. So let's draw them. So we are having, let's say, outgoing cones. So let me write like this thing. So then you are having this thing. So let's say, clear? So this is for outside this thing, outgoing lines. Clear? Okay. So now tell me how I will draw the ingoing photon lines. P equal to constant lines, because P equal to constant lines are what? They are incoming lines. P is equal to constant. Okay, so now look here. What is the slope? Look at this very equation. What is the slope? It's -1. So that means it's like this thing. So it means it's something like this. Okay. So let's draw them as straight lines, because it's a straight line. Okay. So that means this line is what? A continuous line. Ingoing photon line is a continuous line, but outgoing is a discontinuous. So we'll see. So what will be the outgoing here? Anybody? So inside, what will be the incoming line? Incoming line is the same inside, because this is constant throughout, whether it is greater than Rs or less than Rs. So the slope of the line is constant. Clear? So it will be always in this very direction. What will happen? So, and they will end actually at the singularity. Okay. So when you, how I will draw? Yes. So where they will end, outgoing lines, they will ultimately end at the singularity. So let's start from here. So it's like this. Got it? So now let's draw the light cone structure. Light cones. So what are the light cones? So you can think this as the light cone kind of thing. So now it is R equal to Rs. Okay, so let's draw some on this line. Okay, so these are, so this is the direction, P equal to constant lines. So these are actually P equal to constant lines. Okay, and these are what? So these are the outgoing lines. So this is our forward light cone. Okay, like this thing, and this is a light cone. Okay, so similarly here you can draw some line. Let's say here. So this is our light cone. Clear? So what happens? So it will, and this is actually the point of no return. Okay, this R equal to Rs is a point of no return, because what is the direction of the light cone? It will ultimately end up at R equal to 0. Once the particle enters R equal to Rs, so it will always end up where? At the black, at the singularity R equal to 0. And it will never go back. An object, okay, so we call this R equal to Rs as the event horizon. So yesterday already explained it. A compact object having an event horizon is known as a black hole. So okay, so now if you see, it is actually this R equal to R2, R equal to Rs. R equal to Rs. It's actually a one-way membrane in this very case. Okay, whatever goes inside, it will never come outside. So that's why it appears as a black. Clear? So it appears something as a black quantity. Okay, so now you, okay, so this all about this very kind of thing. But still, if you look at this very diagram, these outgoing geodesics are still discontinuous. You are having continuous line is only these straight lines, is it? Incoming geodesics. So but the outgoing are still what? Discontinuous, because this if this This is an outgoing line, so it does not cross R equal to RS. And this outgoing line does not cross R equal to RS. Now the question would be, can I figure out a new kind of coordinate system where I will see these are also what? Continuous. Okay, or in other words, let's put a question this way. Instead of using an advanced parameter, since okay, this parameter P, you can equally think of a retarded kind of parameter. If you remember about the solutions, okay, so this kind of, okay, let me put it this way. This kind of coordinate system we have chosen as an infalling geodesic, for an infalling photon, is it? You can think of a coordinate system which is constructed from an outgoing photon instead of the ingoing photon. So you can equally think of, let's, instead of constructing this kind of coordinate system where, okay, where the photon is, okay, radially moving inwards, you can think, okay, so let me construct a coordinate system with the help of actually the photon moving outwards. So using these very geodesics. So what will happen? Okay, so what kind of structure I will be having? What I am saying, so this kind of diagram or this kind of coordinate system we have constructed with the help of geodesic of an incoming photon which is moving towards the this R equal to RS. You got more the radially ingoing photon. Okay, now you can think, okay, let's forget that kind of coordinate system, construct a coordinate system using the geodesic of the outgoing photon. And try to figure out what is the kind of space-time structure or this light cone structure looks like, how it looks like, or what is its implications. That is equally valid because a light cone contains actually two types of geodesics. One is the incoming geodesic, another is the outgoing. I have constructed my coordinate system from the incoming. Now let me construct it from where? Outgoing geodesic. Clear? So let's do that. Huh? So it is a simple thing. Okay. You have to do the same. Okay, remember we have actually in the Schwarzschild coordinate systems there were actually two radially moving these geodesic null coordinates P. CT is equal to something. You remember that very formula? So we have, so in Schwarzschild we had this kind of thing, CT equal to minus R minus twice mu natural log of R by minus 1 plus constant. What was this thing? So it was incoming photon. And then you had the CT equal to R plus 2 mu natural log of 2 mu plus minus 1 plus constant. Okay, so this is outgoing. From this very thing, we construct actually P coordinate, is it? What I will do, since the trick was to use this constant as a coordinate. So I will use a trick here again. So now my point is construct a coordinate system using outgoing null geodesic. So that is, I will introduce another coordinate Q. Instead of P now I will use Q. So this constant I will use as Q. So that's equal to this CT minus R minus 2 mu natural log of R by 2 mu minus 1. Again here this R will be actually taken from 0 to infinity. It is the same analysis. Do the same thing. Okay. Figure out the matrix. Okay. So at least to do this exercise at your place. Figure out now the matrix the way we have done yesterday. So it will be like this thing, minus 1. Okay, plus minus, it's plus. You need to check actually the it will be actually minus kind of thing. Something minus. There is only the minus change from the previous one. So that was plus in the previous one. It will be minus here because of these minuses. So you'll be having a minus here. Okay. So now you'll be having this. You can do the same kind of geodesic. Okay. So what? Okay. So now let's look. What is our null? Okay. What are our null geodesics? Tell me. Null geodesic means ds square equal to 0. So let's take in the this d theta equal to 0, d phi equal to the radial null geodesic. Radial means you are at a fixed angle, is it? So what it will be? So it will be something 1 minus twice mu by r, this dq by dr whole square. Okay, so it's minus twice dq by dr is equal to 0. So let me. Okay, it is a very interesting case, but it is unphysical. Okay. So what you are having? You are having dq by dr is equal to 0, implies q is equal to constant. So what line is this thing? Q equal to constant. It is an outgoing line. Tisha? Is it? Yes. Okay. Because how? Because we have chosen q equal to constant from the this thing out. So this out. So then you are having dq by dr. Okay, because there are two solutions. You take dq out, so that's equal to something minus twice 1 minus twice mu by r raised power minus 1. Okay, so you can now integrate it out. So I will not integrate it out. So that means this is which one? Incoming. समझ आओ? So now you have figured out two null geodesics. One is outgoing and another is incoming geodesic. Okay. So what is outgoing? So now let's draw this kind of object again in this very diagram. So this is our r and this is our q, and this is, let's say, r equal to this 2 mu business. So let's look in this very region, r greater than 2 mu, r greater than rs. So what is our q? It's an outgoing line. So let's look at infinity first. It's a constant. So it's like this thing. Is it a constant? This is a constant line. This is outgoing constant line. Clear? So what about incoming? At r equal to infinity, it is having a negative slope of -1. So let's forget about this 2. It will be a -1 kind of thing. Okay? Rather, it will be a double of the slope. But I will take only -1. So that is 45 degree. So that's the Minkowski space structure for this line. समझ आओ? So this is what incoming. Now when it will move towards, let's say, move towards r equal to rs. So this line will remain as such. So what will happen to this thing? No. What happens when you move towards it shrinks. So this is the physical principle we have studied. When a light cone moves towards r equal to rs, it shrinks. So that means it closes up. So what will happen? So that means it will shrink a little bit. So this is outgoing and this is ingoing. Now tell me at this object. So what will happen to this line? It becomes perpendicular. So because the slope is infinite. So it's like this thing. Look carefully. Now when it moves inside, so which line is continuous now? Outgoing line is continuous. You can see from this diagram actually, ingoing line is discontinuous and outgoing is what? Continuous. Now look here. So what will happen? It will be looking like this thing. Something kind of this thing. Okay? So what is the trajectory of a particle? Any kind of particle? So it means whatsoever in this very kind of coordinate system, whatsoever particle comes from here to enter, it will never enter this r equal to rs. Okay? So it's where is the trajectory of a particle? It's in this region. So it is in this region. So let's say here. So you will be having a geodesic kind of this for any kind of particle. So it will always move where? In the future. So what will happen here? So it will always move in the future. So what happens to here? It will always move in the future. So that means whatsoever particle comes in this very region towards r equal, in this very perspective, it will be repelled by actually singularity. So what happens? Now look here. So you are having everything moving out of this very r equal to rs. So you are having a kind of object here being formed, while everything moves out of r equal to rs, this horizon, is it? And nothing enters into this horizon. It again becomes a one-way membrane. Everything comes out of this thing and nothing goes inside. So what will appear it when everything comes out of this? Let's say there is a light inside, so it comes out of it. So it's a kind of white hole we call. It's simply a mathematical curiosity. White holes do not exist in nature. You got the point. So this will simply represent this kind of solution. It will simply represent the white hole. It is older now. We call this as a naked singularities. Okay. So this r equal to 0 will represent actually a naked singularity in this case. It will be visible from infinity. Okay. So similarly, now you can draw actually lines. So you will be having the outgoing line is continuous the same way. So there in the previous case, the ingoing lines were continuous. Now what you will be having? Outgoing line is continuous. And the ingoing lines will be discontinuous again. Clear? This you can see actually from this r. So it moves like this thing. It's actually the suffers discontinuity at r equal to rs. So we have now two types of solutions and Einstein equation possesses. Is it? So one we call as a black hole solution, okay, which appear from where? From the event horizon, nothing comes out, and we are having a white hole solution from everything, nothing goes inside, and everything comes outside. Clear? Okay, now let's ask another kind of question. Okay, is there a kind of coordinate system which will take care of all these kind of solutions? Look here, we have to move from one kind of coordinate system to the another coordinate system to look at this kind of things, because we are looking only at a patch of the manifold. We are looking at actually the some part of our coordinate system, because we are not able to explore the entire space-time, entire Schwarzschild space-time. Is it? We are only looking at actually at the part, because looking at the part we get some kind of reality, whether that is physical in nature or not, that does not matter for the time being, but you are only able to acquire the information of the part of the space-time. Now let's think of whether there exists a kind of coordinate system which will give us actually the maximum information of the Schwarzschild space-time. Okay, so it was actually devised very late, I mean 1961, by Kruskal-szekers. Okay, that gives us actually the maximal information, maximum possible information of this, I mean the Schwarzschild geometry or the Schwarzschild space-time. So in other words, so you can put it this way: that kind of coordinate system, this Kruskal coordinate system, gives us actually the both types of the solutions. Okay, so you will be having a solution which contains both naked singularities as well as the black hole singularities. Okay, and you will see there will be actually a copy of the same universe arising here. Okay, so let's look at those kind of solutions. If you have any further question, just tell me here. So I will go slowly in that kind of. So let's move to this. Let's look at these. Kruskal-szekers. It's a German name, Szekers. Okay? Kruskal and Szekers. Shikeris or shikers, something like that. Yeah? Okay. Okay. So let's go to the Eddington coordinate system first. So we are having this Eddington coordinates. So both P and Q, okay? So then R, theta, phi. So this is our coordinate system, where P is actually the advanced parameter we call. Okay, by the way, I forgot to mention the name. The coordinate system, what we have entered there, CT prime, if you remember. Yes. So that CT prime defined as P minus R, is it? This is actually known as Totai's coordinate system. Is it the correct word? Totai's? Marmasha? Sorry. Huh? Kashmir. Yes, that's fine, huh? Okay, Totai's coordinates. So what we have here, P is actually equal to CT plus R plus twice mu natural log of R by 2 mu minus 1. What this is? It is advanced parameter. Huh? We call it as an advanced. Okay. And then you are having this Q is equal to CT minus R minus natural log of R by 2 mu minus 1. So this is known as retarded parameters. Right? So now what we'll do, we'll first write our Schwarzschild matrix in terms of this P and Q. So what we'll eliminate? We'll eliminate T. So we'll put actually now the line element in terms of this P, Q, R, theta and phi. So that means we have written, if we are able to do so, we have written our Schwarzschild line element in terms of the Eddington coordinates. Got it? So let's try that. How to do that? If you look at this thing, so let me take therefore this P minus Q. So what will be P minus Q? CT is removed, is it? So it is something twice R plus 4 times mu natural log of R by 2 mu minus 1. Okay? So R, in other words, so let me write this as half here. Okay? So remove this 2 and put this 2. Clear? समझ आओ? Now से कहते हो differentiation में figure out the elements, coordinate elements. So let's write it as half R. So it will be dP minus dQ. Coordinate differential, because if you figure out the line element, you need to figure out coordinate differentials. So what it will be? dr. So now the differentiation of this thing, it is twice mu divided by r by twice mu minus 1. Then it is differentiation inside, so it's 1 by 2 mu dr. Clear? You sure? So what you are having? This 2 mu cancels. So now you are having dr common. Okay, so you multiply them. So it's r by 2 mu minus 1 plus 1 divided by r by 2 mu minus 1. So how much is that? So it's simply 1 minus twice mu by r raised power minus 1 dr. Okay, because this cancels. So it's r by 2 mu divided. So it's 1 minus 2 mu by r. So that's what I have put in this way. Clear? So now what we have figured out? Okay, so r you can write now. dr is equal to half of 1 minus twice mu by r raised power. Sorry, not raised. dp minus dq. You square it. Okay. Clear? Also, what is p plus q? So okay, so now you square it. So what you get? So which implies dr square is equal to 1 by 4, 1 minus twice mu by r square. So it's something dp square plus dq square minus twice dp. Okay. Similarly, we have this very object. Now let's add them. So also you are having P plus Q. How much is that? Twice CT. Is it? So you add them, only the T will be there. So what you get? So in other words, half of this very object is like this thing, which implies C dt is equal to, or rather C square dt square is equal to 1 by 4. So it is dp square plus dq square plus twice dp dq. So I have ignored one step. So you take first dp and dq, then square the two. Okay? So everybody followed it? Good. So now let's substitute it here in this line element. So we have this ds square is equal to minus. So you are having 1 minus twice mu by r. Okay, c square dt square. What is that? So it's 1 by 4. Okay, dp square plus dq square plus twice dp dq. Then you are having plus 1 minus twice mu by r raised power minus 1 dr square. What is dr square? 1 by 4. Okay, into 1 minus twice mu by r raised power 2. So it is dp square plus dq square minus twice dp dq. Okay, so then you are having plus r square d omega square, because theta and phi does not change. Under these, it is simply the radial coordinates where we are looking at. So now simplify this thing. So what you get? ds square. Can you tell me? Nazar se मैंने कही को minus. समय नजर कम जो है like this thing dp dr plus r square. Now look here how beautiful this matrix looks like. Okay, because everything will cancel out. dp square d, it comes with minus sign. This dt square dq square comes with the plus sign, and this minus 1 plus 2 is 1. Okay, so it is this very object, and 1 by 4 is sitting, and this is 2 plus 2 is 4, and 1 by 4 is sitting, so it's gone. Okay, समझ आओ? Okay, so now, okay, now if you see, okay, so let me, for the time, let's call this as equation 1. So this is our equation 1, because I have put no equation numbers on this side. dp dq, yes, dp dq. Good. Okay, clear? So if I am in the radial plane now, where theta and phi are fixed. So if this theta and phi are fixed, so that means we are only in the radial plane. So we are taking a section of our geometry. Okay, so in that case, this d theta is equal to 0 is same as d phi. So what will be this ds square? So it is minus 1 minus twice mu by r. Okay, dp dq. Okay, so this is just for the simplification. Okay, to be for the time being, to keep it away, this very factor. But at the end of the calculus, we can keep it back, because it is not affected anywhere. So that means when you are thinking of a patch, it's actually not a radial plane, it's actually a sphere entire thing. So not that so much. So because you are taking only one slice of that, it is in reality the entire sphere at that very point. Okay. So now if you see, you are having dp and dq being multiplied. So that means it's an off diagonal kind of object. Matrix is off diagonal. Diagonal would be only the diagonal terms, dp square, dq square. Okay. So what to do in order to remove this kind of problem? Okay, now we will introduce a kind of coordinate system. No. I have said something wrong. Those were not taught as these coordinates. That's right. So we have to delete it. Those were not taught as coordinates. Okay. So now I am going to introduce actually. So now let's introduce Okay, so it takes a little bit time to understand why these transformations are required. Okay, so once you do it 2-3 times, these kind of calculations, you will actually understand why we require. Okay, look here. So we have, okay, so we have to actually look at the pathologies of this Eddington coordinate system. Those pathologies we have discovered from the space-time diagram. Either one type of lines are continuous or the other type of coordinate system. Now we are moving to the another kind of coordinate system. Okay, or rather we are actually writing, we have not yet moved to the another kind of coordinate system. We are simply writing our line element in terms of those Eddington coordinates. Okay, when I am writing in terms of the Eddington coordinates, what happens? This is actually completely off diagonal. So what could have been it? So it is like this thing, dp square, dq square, and then you are having dp, dq. What could be the matrix? So dp square term is not here, it is 0. dq square is not here, it is 0. What is this thing? So you are having actually 1 minus twice mu by r kind of thing. Okay, rather half. Okay, and half is here. So then they will add to make a 1. So this completely off diagonal. To make it as a diagonal, so let me introduce a new kind of coordinate system. Okay, or let's write in terms of the time-like coordinate and the space-like coordinates. T and R kind of coordinates again, but in a new fashion. Okay, so let me introduce. And one more point, since this P and Q are actually null coordinates, we are moving from null coordinates toward time-like and space-like coordinates, T and R. Okay, so let me write. Let me tell you what I mean by that. So let's transform. Let's introduce. Okay, this CT is equal to half of. It is the same thing, P plus Q, and another kind of coordinate system. Let me write it as R tilde half of P minus Q. So how much is that? So it is R plus twice mu natural log of R by 2 mu minus 1. So let's call this as equation 3. Okay, so we call this as, since this is now, if you look at this, is actually the standard Schwarzschild time. Is it? Is it? Why? Because if you take the sum of that P plus Q, somewhere we wrote P were in terms of actually CT and Q was also in terms of CT. That CT in those things were Schwarzschild time. Is it? So now that means this P plus Q will give me what? CT. That is simple sum. Okay, it is the same thing. Now what this R tilde gives me? So this actually is Schwarzschild time. Clear? This T. That's why I have not put a T tilde here. And R tilde is not that. Schwarzschild, this radial coordinate. So sure? Is it? So we call this as a tortoise coordinate. And this is our new radial coordinate. Now let's look at in this very thing. Now you will see actually something, I mean, curious is happening. So let's calculate what I have to calculate, dp and dq. So if I now calculate dp and dq, okay, so now let's calculate in terms of this CT and R tilde. So what you will get actually, so now we have been doing all this thing, ds square will be something, this factor will remain as such, rather 1 minus twice mu by R kind of thing. I think square will come out and it will be something c square dt like this minus, and this will be plus dr. So when I change it from where? That dp and dq to this t and r tilde. So what I got? So this kind of metric. Okay? So it's actually, since I am considering only one theta and phi, so it's actually there will be this term as well. So that I am not taking into account. I will put it at the end of our calculations. So now while I have started, so this is a very important point. It is not square here, I'm sorry. It's not. So let me write it first like this thing. Omega square kind of thing. Omega square R, because this depends on R. So then you are having minus c square dt square plus dr square. This is very important thing, so which I want to explain. So you have Schwarzschild geometry. That's a curved geometry, is it? Samajh? Now you have mapped that geometry in such a way you have constructed actually a map of that geometry, let's say on your plane, is it? And that looks how? That very object. Forget about this omega. What kind of that is? That's actually the Minkowski space-time. Is it? So that is c square dt square dr square kind of thing. Clear? So that means you have mapped your geometry in such a way to where? Minkowski space geometry. Except a scale factor. So we call this as a scale factor. It is known as a conformal factor. Forget about that. That means, so this is a kind, this very factor, this represents simply zooming in and zooming out of the same thing. Let's say I will give you a sheet of paper. Okay, you zoom in or zoom out, what you will see? At a different scale, you will see actually the same structure. Clear? So that means any kind of geodesic, what you will be able to calculate, so that will remain same, whether you zoom in or zoom out. So that means our space structure, when I have transformed actually, rather I should say a patch of that geometry to where? Minkowski space geometry. So what will be now the null geodesics here? Null geodesics will be put this equal to 0. So that means it is the simple Minkowski space light cone. Got it? Huh? So why this is known as tortoise coordinate system? You can think of a tortoise. So look at this thing. Your hand back, that's curved, is it? So where it is projected? Look at the bottom of the kashwa. So where it is projected? On a flat surface. That means you are projecting actually the part of that geometry on where? A flat surface. So that means this very coordinate helps me to map my Schwarzschild geometry to a flat Minkowski space. It's not the entire geometry, it's actually the part of that very geometry. Think of, okay, so usually these things are being done through the differential geometry because that helps us to understand what exactly is happening. So let me give you actually this kind of example. Think of a sphere. This is our favorite example, okay? So you take, let's say, a map of a given country on the sphere. Okay, let's say our J&K. So you want actually to draw it on a plane. How you will do it? So you make actually a coordinate transform, a mapping from your actual point, that is our J&K, to some local chart, is it? And you are able to figure out one chart. That means you are able to figure out one part of your geometry onto a flat space. And this way you can construct actually the entire geometry. Clear? So that's what exactly we have done here. Okay. So now let's look. Okay. So but unfortunately we are having a problem again here. So why actually this? So we are still in the actually in the interplay of the Schwarzschild and Eddington coordinates. Is it? Have I introduced any new kind of coordinates? We are still in interplay of this P and Q and CT and R. Is it? So sure. Now there is actually a topology in this very ds square. Although I have mapped it where? On a flat geometry, but there is again a problem. Can anybody figure out the problem in this very line element? At r equal to 2 mu, it becomes 0. So look here, there is no metric element where? When you put r equal to, that means it's not a defined quantity where? 2 mu. That means at the Schwarzschild radius, it's not defined. Clear? So that means this is our monster. This 1 minus this omega, it is a monster for us. We need to remove this kind of monster. So it is actually this very point where Kruskal comes. Okay, this case people come and to eliminate this very object. Samajh? Got it? So we need to figure out actually a transformation which will help us to eliminate this object. Samajh? So numbering for what size? So this was 3. So let's call this as 4. Call this as 3. Clear? Okay. Any problem? Okay. So let's have a pause. So let's call this as 5. Okay, what is our main motivation? We need to remove pathology in equation 5 at r equal to that's good. Okay, so how to do it? Now let me introduce a new kind of coordinate system. Okay, so we introduce a new coordinate system. Let's call that as P tilde and Q tilde. For the time being, there will be r theta and phi as well. Okay, but I will not be bothered about that. We'll put everything at the end. So that means this P tilde is a function of P and Q tilde is a function of Q. Clear? So let's look at from equation 3rd. Okay, so I will write this ds square because we have gone to equation 5 from this equation 3rd using these tortoise coordinates. Clear? So samajh aaya? So I will start from here. This is very useful. So we have 1 minus twice mu by r, this dp dt. Clear? So what I will do, I will divide it by dp tilde and dq tilde and write now the metric value. So if I know these differentials, if I know this derivative, what I have done, I have actually expressed this ds square in terms of the new coordinates. Samajh aaya? Yes. Okay, what is our need? I need now to choose this p tilde, q tilde or p and q in such a way that it removes this factor, because this factor is being carried over to this very object. Samajh aaya? Okay, so what Kruskal found, okay, we can derive it, but I will introduce only. Okay, so Kruskal found, so we need to choose P and Q such that 1 minus 2 is removed. Okay, so this very factor is removed. Okay, well, how to do it? So this is the attempt of the Kruskal. Clear? So what he found, so this p tilde, if I can write it in this form, p by 4 mu and q tilde as minus e raised power minus q by 4. So if I write my p tilde in terms of p like this thing and q tilde in terms of q like that, so then I am able to remove this very object. So whatsoever coordinates transformation we have done, if you see, r equal to 0 is everywhere singularity. That is, in no coordinate system we are able to remove this singularity. This we call as an essential singularity, is it? And in every coordinate transformation we see r equal to 2s, this 2 mu is a regular surface. Got it? It's a regular point. Okay, so now let's calculate these things. We have simple mathematics now. There is nothing. This is almost a okay done. So let's try it. So let's calculate what will be this p now from here. So what will get p? Let's calculate p. So how much is that? So it is 4 mu natural log of p tilde, is it? So what is q? So q will be minus 4 mu natural log of minus q tilde. Is that true? What I have to calculate? dp by dp tilde. So therefore this dp by dp tilde. How much is that? So it is 4 mu by p tilde. Tisha? So let's write p tilde back. So it is 4 mu. What is p tilde? E raised power p by 4 mu. But it is in the denominator. It will be e raised power minus p by 4. Clear? Samajh aa? Okay. So now what is our this dq by dq tilde? So it is this minus 4 mu. Okay. Then you divide it by minus q tilde. Clear? Differentiation. So what that is? Minus and minus goes. So it is 4 mu. What is q tilde? It's in the denominator. So it will be equal to minus will be there because q tilde contains minus. So it will be here simply q by 4 mu in the numerator. Samajh aa? Clear? Everybody followed it? Okay. So now let's write. Therefore, let me calculate this quantity first. Therefore, dp by dp tilde, dq by dq tilde. So let's call this equation as, what was the equation number? 6. Okay. So what will be that equal to? Now let's calculate it. It's 4 4 60. So it is 60 mu square. Clear? Tisha? Then e raised power minus like this thing 1 by 4 mu p minus q. Can I write it? Can I write it? Can you tell me what is half of? Okay, so if you remember from your previous formula, what is half of this p minus q? So we just wrote it. It's something r plus twice mu natural log of r by 2 mu minus 1. Is that true? So if I divide it by now 4, so let's divide it by 4 mu. So what it will be? So it is twice mu. So this will be gone. Clear? Teacher? So it is like this. Okay. So now what you write it? So you are having now 16 mu square exponential r minus first term is r by 2 mu. Clear? Then you are having, because it is additive, it is exponential r. Okay. Minus natural log of r by 2 mu minus 1. Okay. So you can take this minus 1 here. So it will be simply equal to 16 mu square e raised power minus r by 2 mu. Okay. 1 divided by r by 2 mu minus 1. Samajh aa? So now what you are having here? 1 minus twice mu by r. You can take r by 2 mu out. So not that sum. So what that is equal to? So it is simply r by 2 mu will come out. So this 2 mu will go up. So it is 32 mu cube by r cube. Okay. E raised power minus r by 2 mu divided by 1 minus twice mu by r. So now use this result in equation 6. Okay. Using this result in equation 6. So what we get? Therefore this ds square is equal to minus 32 mu cube by r. Then you are having e raised power minus r by 2 mu dp. Okay. So where is the singularity now? Where is the singularity? 0. It's at 0. Okay. This is very important. Okay. So now let's look at the useful form. This is not a useful form of the matrix. Why? Because it's off diagonal. Clear? So, so now look here, you are having a factor. This kind of factor is multiplying everything. Okay. So I want to put it in a useful form. So because the useful form, what we have figured out in a previous way, in the previous moment, that was actually the Minkowski space-time. Is it? With a scale factor, but that was a pathological factor. And we want to do the same thing here. Now the pathology we have removed at r equal to rs or r equal to 2 mu, that is being removed. Is it? Now we will put this very element into some useful form. Clear? Samajh aa? So let's look Okay, so let me introduce. Okay, the end result I will ask in the examination. Huh? These things I will not. This I will not ask. Only the end result of this problem will be asked in the examination. Okay, so be relaxed. The paper will be very easy. So let's introduce now. Introduce this mu is equal to 1 p tilde plus q tilde the same way. So u is equal to half of p tilde minus q tilde. If you see now, yes, it's simply a transformation. Huh? The same way what we have done earlier. What was that transformation? That was same as p plus q and p minus q, is it? Tisha, we are doing the same thing. Okay, we call this v and u as the Kruskal-szekers coordinates. These are known as case coordinates. Huh? So let's try it now. So you can now calculate this d. Okay, so you can see from here this dv square minus du square is equal to dp tilde dq tilde. So just take minus here because in these things p square q square will cancel, only p q will survive. Now look here. So you have written this in a nice form. Okay. Okay. So therefore, there is one point. Okay, that I want to mention. So we need to figure out what is the relation between v in terms of this p and q, and what is the relation of u in terms of p and q. Those were the original coordinates, is it? Null coordinates. Then we will seek the relation between the actual Schwarzschild coordinates and these u and v. This is simple, just manipulation of this very formula, nothing more than. I will not introduce now, nothing more. Nothing more will be introduced. Okay, so let's, if you see now, so let's write this first. So which implies therefore this ds square is equal to, so what it will be now? Minus 32 mu cube by r e raised power minus r by 2 mu. Okay, so now this object is actually dv square minus dv square. Now if you see, it is again the Minkowski space-time, is it? That was actually in terms of p and x, t and r. Now it is in terms of v and u, except this very factor. Okay, so this you can say it is a global scale factor, but it is regular everywhere except at r equal to 0. That is actually black hole singularity. Now we were looking only this for the, fixed theta and phi. Now I will write that very for any theta and, so let me write that very. Samajh aa? Because this is not affected anywhere. Okay. So now let's calculate this. Okay. So we'll see in a moment. So what is the, is this 8? 7. So first we will see what is the relation of this. Then we'll look at the geodesics. Okay. So we are almost there. No problem. Now let's first look at what is this u square minus v square. Let's calculate this very object. Okay. So let's calculate this thing. So it is 1 by 4 p tilde square plus q tilde square plus twice p tilde q tilde minus 1 by 4 p tilde square plus q minus twice. ये चाहे नियम पद कैसे क्लास? हैं? So what is that? P tilde q tilde. What was p tilde? Anybody? E raised power p by 4 mu. What is this thing? E raised power minus q by 4. So what is that equal to? E raised power 1 by 4 mu. So let me write p minus q. So what is this p minus q? Just we have calculated. So that's e raised power 1 by 4 mu p minus q we have calculated, is it? So what was that equal to? R by 2 mu plus or minus plus natural log of r by 2 mu minus 1. Okay, so how much is that? So it is r by 2 mu minus 1 e raised to r by 2. Okay, so this is very important formula. This u square minus v square. Okay, so this will help because where is the trajectory now? Trajectory is our trajectory is in the UV plane, is it? Instead of TR plane, it is where? UV plane. That's why we need to figure out what kind of trajectories are allowed. Okay, so we are having this very formula. So this I'll put here. Square minus v square is equal to r by 2 mu minus 1 e raised to r by 2. So r is for or u it is minus, it's minus. This subject is like, yes, it is minus. It's minus. P minus q is minus times. Compare this thing. So you will see in a moment why it is necessary. Okay, because I need to figure out the trajectory. Okay. Now let's write what is our v. It's half of p tilde plus q tilde. So how much is that? Half of what is p tilde? E raised power p by 4 mu plus, sorry, it is minus e raised power minus q by 4. Isha? Is this the case? So can I come on ticket for Gamu simplify? Okay, so we have actually, okay, yes. So what I want to do, I want to put this P and Q in terms of our original coordinates, in terms of the Schwarzschild coordinates. Samajh aaga? So what are those? So e raised power, what is P? So it's 1 by 4 mu. That is Ct plus r plus twice mu natural log of r by twice mu minus 1. Tisha? Then you are having e raised power minus 1 by 4 mu. Q is how much? Ct minus r minus twice mu natural log of r by twice mu minus 1. Here I want to actually figure out what is the relation between this u and because I know the trajectory in the Schwarzschild coordinates, is it? Schwarzschild coordinates gives me the coordinate type and what? The radial coordinates, is it? So I want to get the meaning of this v and u in terms of those very coordinates. Samajh aaga? So that means I can actually relate my Schwarzschild type space time and this Kruskal-szekers space time. So samajh aaga? In this very, everybody is following it? So what that is equal to? So it is half of okay, Ct is so you are having here plus Ct and there is a minus Ct, is it? Now you are having plus r, it is plus r plus r. So what you take out? E raised power r by 2 r by 4 mu. R by 4 mu take out, then you take e raised power twice mu and mu will cancel out. So it's 1 by 2 natural log of r by 2 mu minus 1. You take them out. So what remains inside? So inside remains e raised power Ct by 4 mu minus e raised power minus Ct by 4 mu. So what this object is? Divided by 2, it is sine hyperbolic. Clear? Isha? So it is sine hyperbolic. Okay. So now the point is here. Here is an important point. Now I will choose, okay, since when you take the root up, okay, so let's take the root up. So this half will come here, okay, so this half will go here, is it? So you will take root only when this object is positive quantity. So you cannot take root if it is a negative quantity. So that means, so therefore for r greater than 2 mu. So if I take r greater than 2 mu, since there was actually, if you, so I have, it's actually a modulus, and that is exactly the thing, right? So what I am trying to say, so it's actually the modulus of this thing. So when you take the modulus, so when you take the root of this very object, you take, let's say if r is greater than 2 mu, then it's a positive quantity. So it's simply a modulus function. So therefore, so I can write this v is equal to, So what this will become? E raised power, okay, so it will become something r by 2 mu minus 1 raised power half. Clear? So this becomes e raised power r by 4 mu, and this becomes actually sine hyperbolic ct by 4. This is, if you see, this is actually the relation between what? T, r and v, is it? T is a Minkowski space time coordinate. Sorry, T is the Schwarzschild time coordinate and V is our the Kruskal coordinate. Clear? So this is the relation. Now similarly you can take U. So let's take U. Okay, so this is for r greater than 2 mu. Okay, for r less than 2 mu. So let me write for r less than 2 mu. What will be nu? So similar, what you have to do? You have to interchange 1 and this thing. So that you will put it as 1 minus r by 2 mu. So it is simply 1 minus r by 2 mu raised power half. Okay, e raised power r by 4 mu. Okay, sine hyperbolic ct by 4. Samajh aa? So now you can calculate what? U also. U is what? Half of e raised power this thing with a minus. So that will become plus. Only which factor will change? This factor. It will become cos hyperbolic. So everybody got it? So let me write now. So what we have at hand. So we call now this V, okay, for r greater than 2 mu. So we are having V is equal to r by 2 mu minus 1. Okay, e raised power r by 4 mu. Okay, sine hyperbolic ct by 4 mu. U is equal to r by 2 mu minus half raised power half e raised power r by 4 mu cos hyperbolic ct by 4. Okay, so yes, now let's write V. Let's write for this r less than 2 mu. There are interesting relations you will see. So for r less than 2 mu, so what we have, so this V is equal to 1 minus r by 2 mu. So at least memorize this very coordinate system. So this I will at least ask. Okay, sine hyperbolic ct by 4. So U is equal to 1 minus r by 2 mu raised for half e raised for 4 mu cos hyperbolic ct by 4. So also it can calculate. So now I am done with the calculation. Then we will do only the physics. So therefore, for r less than, okay, so r greater than 2 mu, what is our V by U? So V by U is equal to tan hyperbolic ct by 4. Rest cancels. And for r less than 2 mu, so you are having U by V is equal to tan hyperbolic ct by 4. Samajh? Whether you introduce your coordinate system in this way or that way, so it's okay. So we call this, so this is a relation between this V and U and the Schwarzschild coordinates. So this kind of coordinate transformation is known as Kruskal-szekers Coordinate transformation. Samajh aa? Now let's look at the interpretation of these things. Okay. So let's look at the null, radial null geodesics. So that means we'll ignore this very part. So because what I require only these things. So this very objective. Okay, so let me keep it there. So let's keep it at bottom. So what is V square minus U square? What was that? So r by 2 mu minus 1 e raised for r by 2. So this, let's write them at the bottom because rest board I require. Okay, so let's look at the null radial null geodesics. So what are those means? So that means this very object is equal to 0. So it means dv square minus du square is equal to 0. So let's integrate it out. It gives me v is equal to plus minus 0, plus a constant. So is it true? So you take it and then integrate. So what it gives me? So that means the radial. So you can take plus as the outgoing photon and minus as ingoing photon. Clear? So it means what is the angle of inclination? So let's draw the plane. So you are having this. Let's say this is your V. Let's write this as U. Okay, we'll see in a moment. So what is our the radial coordinate? So it passes through the origin, is it? This geodesic pass through the origin, is it? Of that VU coordinate system. So it means what is the angle? Angle is 45 degree. Eh? So slope is like this. So you are having. So this is our now geodesic. Let's call this line as V is equal to U. And what about this line? So we need to interpret these things. So this gives me what? V is equal to clear? Because it's now the flat space. Eh? You take an event at somewhere and look at these things. Eh? What's happening? So what this? Now what I need to calculate next? Anybody? Now let's look at the lines of constant R and T. So let's look at in this very thing. So since V and U are related by those kind of relations. Now let's look. I need to figure out what is the trajectory of the particle in this very diagram. How it looks like. So that means I need to look at the relation between V and U. Okay. Now if you look at the first relation between V and U. Okay. So you see it is x square minus, so this kind of relation is like this thing, x square minus y square is equal to some a square for the timing. For whatever it's function of r, let's say it is a, okay. So what this is? It's a square hyperbola, clear? So in other words, let's take, so let's look at constant curves, curves for constant R and T. So if I now fix my R and T, let's say at a given point, so what means here? Let's say whether it is in the R less than 2 mu region or greater than 2 mu region, you fix some point, okay? So that means this is a constant thing. So how it looks like then? It's a hyperbola. So that means, so at that point the trajectory will be always what? A hyperbola. So it means, so it gives me, we are having these constant R and T curves. Sorry. So R hyperbola. So like this thing. So V square minus U square is equal to some constant. So you got some? Okay, so I should not take T because I should look at for only R. Constant R curves are hyperbola. Where are those? Tell me. Where this V square minus U square, it's actually hyperbola. Hyperbola is having actually two branches, is it? So summation where it will be. So this is the hyperbolic region. So this is actually y square, x square minus y square is equal to a square, is it? So this is the branch. Okay, so so we'll interpret in a moment what is going on. So that means, so in this VU plane, now these are actually the trajectories. So since these are the constant R lines, is it? So that means constant R takes the values in terms of the mass, is it? So R can take value, let's say R is equal to 2 mu. Can it take? Okay, so it means, so let's say this is R is equal to 7 mu, for example. Let's say this is R is equal to 6 mu, and so on. These are the constant values, because we will measure R in terms of what? This schwarzchild radius. So much, how much is it? Clear? Okay, so now, so this will give me actually the geodesic. What it will give me? Simply the trajectory of the particle moving in which Schwarzschild space-time. where it is. So it is actually outside, since if I am taking r, let's say greater than 2 mu, so this object is a positive quantity, is it? So that means we are actually outside the black hole. Clear? So we are actually outside this, Schwarzschild radius. Clear? Now let's say if we are reaching r equal to 2 mu. So let's look at third point at r equal to 2 mu. So what is happening? V square minus u square is equal to 0. Clear? So what it gives me? V is equal to plus minus u. So that means this V is equal to u is a straight line subtending a 45-degree angle. Is it? The light cone line. Is it? So it becomes actually the asymptote to these hyperbolas. Is that true? So that, in other words, these lines are something. These are actually what? Asymptotes to our hyperbola. So it means this line and this line, this and this, they represent simply our event horizon. These the asymptotes in this very diagram are what? Event horizon. Event horizon is described by r equal to 2 mu. So I will call this as the event horizon. So we'll match it with the accelerating frame as well. Huh? The starting result we can discuss it. Okay. So because that you are having the same kind of trajectories there, eh? Except the one important point. Now let's look at r equal to 0 point. Okay, let's look in this very coordinate system where r equal to 0 point is located. Samajh aa? What is r equal to 0? A black hole singularity. Let's look at where that is located. Then we'll go to the constant t lines. Okay, so it's 4. So let's look at r equal to 0 point. So it is mapped. So now put r equal to 0 in this very equation, is it? So what that is? V square minus u square is equal to 1. Is it? So what it gives me? V is equal to plus minus root of u square plus 1. Is it? Is it? Is it clear? So when you put r equal to 0, actually there should have been a minus 1. So it will be actually 1 minus r by 2 mu. Huh? So you need to check. There is actually a minus which we have missed. Yes, that contains p tilde multiplied by q tilde, is it? So that contains a minus sign that we have missed here. Huh? Please check, it's a minus sign here. Why? The reason being, if it is not a minus sign, then these are not the hyperbolas in this very region. Huh? They will be hyperbolas in this region. Just check it. It's a minus sign. Eh? It's something minus. Please check. Then this is actually positive. Now tell me how many solutions are to this very equation? Tell me how many solutions are to this very equation. What is the point? R equal to 0. You are having a single point. It is mapped to 2 lines. Rather to 2 curves. Okay. Where it will be? This very curve. One curve will be like this thing. Another curve will be like this thing. Because it is in these lobes. So what is this very point? This is equal to r equal to 0. So this is our black hole singular. And this is also what? So this will turn out to be actually the white hole singularity. Okay. So this diagram is known as Kruskal-szekers diagram. Here's diagram. So it gives you actually the maximal information about the Schwarzschild geometry. Okay. So now let's look at the constant t lines. So where I can get constant t lines? From here, from this very relation. Is it? So let's take t, okay. Let's take t equal to minus infinity line. When t equal to minus infinity, what is tan hyperbolic? Because you are having two relations for r greater than 2 mu, you are having v like this thing, and r greater than less than 2 mu, v is like this thing. Now let's figure out constant t lines, because okay, we have figured out r coordinate. These are the curves of what? Constant r. Constant r means you are looking at a trajectory in the usual Schwarzschild geometry. On this very diagram, it looks like what? A hyperbolic curve. Samajh? Now I need to measure as well as the coordinate time. Clear? So I need to look how that coordinate time looks like. Samajh? So wire is actually, I need to figure out wire is t equal to 0 line. Now can anyone tell me why is t equal to 0 line? When r is equal to greater than, okay, so let's look at t equal to 0 line first. So a part, t equal to 0 line. So why is this, in this very diagram, why the Schwarzschild time goes to 0? So let's look at r. Okay, so for r greater than 2 mu, so when this is equal to, so when you put t equal to 0, what this becomes? 0. So that means v by u is equal to 0. So what it gives me? V equal to 0. Samajh? Now tell me which line is v equal to 0? It's along u. So it's along u. Okay, so this is our what? T equal to 0 line. So this is our t equal to 0. Clear? For r less than, sorry, r greater than 2 mu. So now for r less than 2 mu, what you are having? U by v is equal to 0. So what it gives me? U is equal to 0. So that means, so this very region, you should now understand, this very region gives you the outside the black hole, and this very region will give you what? Inside the black hole. Samajh? So you are having, this is the region for what? T equal to 0. Okay, so this is the t equal to 0 for r less than 2 mu, and this is t equal to 0 for r equal to 2. Now let's look at the other, now the lines. Why is t equal to infinity and why t equal to minus infinity? Samajh? So let's look at. So let's look at t equal to minus infinity first. Can anyone tell me why is t equal to minus infinity? In both the cases. What is tan hyperbolic minus infinity? Yes. Yes. Minus 1. Yes. Good. So this will become minus 1 in that case. So we'll be having in that case v equal to minus u. So that means this very line. So this line becomes t equal to minus infinity. The asymptote. Okay. And similarly you can take t equal to plus infinity, that's equal to v is equal to u line. This very line. So this is our t equal to plus infinity. Now that means, look here. So this region is from where? T equal to minus infinity to 0, is it? So it means all the lines are where? Other t lines are within this very region. So the constant t lines in this region will be like this thing. So these are the constant t lines. So these are actually constant of t. So this thing. Constant. Everybody followed it? Samajh? Similarly, you can extend it on this very side. Constant t lines. Samajh? What will be minus infinity on this very side? It's here. What is the plus infinity? It's here. Because you have to look at this very region. Samajh? So this is a minus infinity line. This is what? So in other words, this is actually this object, or rather this object is actually reverse to this thing, inverse of this thing. Samajh? Got it? Okay, so now let's interpret this very diagram. What exactly? Wait a second. Okay. So now look here. So we have constructed a diagram based on Kruskal-szekers coordinates. So it gives us 4 regions. Is it? Is that true? So what is the region 1? So let's say this is a region 1. This is, let's say, region 2. This is region 3. And this is what? Region 4. Samajh? Okay. I am almost done. I mean, just need to interpret this very diagram, what it means. So this is your usual. Okay. Forget about the region below this thing, this line. Okay, so don't take this very line. I mean, take this line above everything above this thing and forget about this thing for the timing. Clear? So now look here. So that means this very region is actually the outside the Schwarzschild radius, and this region is where? Inside the Schwarzschild radius, and you are having a black hole singularity here. Now that means if a particle comes, let's say, follows a certain kind of trajectory, let's say, a particle follows a certain kind of trajectory, let's say, so this could be a trajectory. It is possible that it may fall where? It may follow towards a black hole singularity. Once it reaches towards R equal to Rs, it will fall where? Black hole singularity, is it? And now look from at this very diagram. Let's say you are having a stationary observer somewhere sitting, clear? And he is observing the radiation that is emitted by this very observer. Let's say you are having this an infalling observer. He is moving. So what will be the space-time? I mean, these light cones. Light cones will be simple. These are actually the. I mean, they will be actually like this. Like this, straight. I am not able to draw them. So they will be straight line. I mean, these kind of cones. Now let's say it emits a radiation. Clear? So let's say an observer, it emits a radiation once it goes through. So there is an observer at infinity. So it means he will observe this kind of radiation. It is all outside R equal to Rs. Samajh? So now, so wherever he goes, so the observer who is sitting at infinity observing this infalling observer, he will always observe it. Samajh? Now once the observer moves towards where? When he reaches to R equal to Rs. Samajh? Let's say the person reaches where? R equal to Rs. So he may, okay, so first instant at the infinity he may actually observe this very radiation, that is he is falling towards what? R equal to Rs. Now once he, okay, so where is the curve now? So it is close actually to this very, I mean to this very asymptote. Samajh? So that means if he is emitting a radiation, it will never reach to where? Observer. It will actually take infinite time for an observer to get that very signal. Samajh? Now if this observer drops into this very, let's say, in this very region, so even though he emits the radiation, this radiation, because it has to follow this, I mean this light cone line, so it will never reach to the observer at infinity. So that means this very object becomes the point of no return, the event horizon. So Samajh? And you are having, okay, so this is our R less than Rs region, and this is actually R greater than Rs region. Now let's look at this very thing. So this is our black hole singularity, what we already know. So now let's look at this thing. Now you can have an observer here, he may send a radiation, is it? A signal. Once he sends a signal, it will be seen at infinity as well. Samajh? Because this region is opposite to this thing. So let's say if he sends an observer is sitting at infinity, he may observe this kind of object, what we call the white hole. Okay? Samajh? So that is, in this diagram you are having both black hole solutions as well as white hole solution. Now what about this thing? So this is exactly the same thing as this thing, but in the reverse order. You can think this is another universe having the same kind of dynamics. Okay? I will not call the universe. So you are having two space-time regions where the dynamics are actually opposite to each other. The way you have having here the dynamics, you are having opposite to that, reverse kind of thing. And they are connected. Okay, so there is no possibility. Now look here. Now if you are having some observer here, he wants to cross to this very region. Is it possible to cross? Now let's look from this very diagram. He may cross, but he will ultimately enter into this very region. And these lines are actually points of no return, and he may be trapped here within the black hole singularity. But if he crosses from this way, since this is a white hole or the naked singularity, it repels the particles. Clear? So that means he will never be able to cross this region or this region. Samajh? Now is there a way to connect the two regions? Samajh? So that means this observer has to go to the infinity and come back to this very region. So this is one possibility. That is an impossible thing. And there is another thing, a good concept of actually when we, and that's actually quite true. So these two regions are connected by a kind of structure, what we call it the wormhole. Samajh? And what is actually the wormhole? I will tell you. Since this diagram we have taken only the slices in theta and phi plane, clear? So, but if you think it as an embedding in a higher structure, Okay, think of the surface of the sphere. It is embedded in a three-dimensional region. You know, surface. The sphere itself is a three-dimensional object, but the surface is what? It's an embedded object where? On a three-dimensional region. Clear? So similarly, you can think this as, since if we are in the four-dimensional space-time, this is a slice. Okay, but if I extend it in the look, let's figure it out how it looks like in the three dimensions or in the four space-time dimensions. Clear? So it looks like a kind of bottle. In a sense, you rotate it. Simply rotate this very object. Okay. So let me draw the diagram only. Okay. So I will not go to the mathematics because we are already too late. So let's take the constant of phi values and constant u values. So you can look at this kind of region. So this is one of the slices, phi slice. Okay. So this what we are doing. We are slicing the phi coordinates. Is it radial infall motion? We are taking only the one phi. Then we'll take all these kinds of phi's. So what will happen? So you will ultimately, let's say, so there will be another kind of phi slice. There will be another kind of phi slice. Okay. So let me erase these things. I am not good at drawing that. So okay. So let's draw. So this is a constant phi. So this is some constant phi slice, and let's draw these trajectories. What should I say? Constant u lines, because ultimately where we are in the UE plane. Let me draw the constant u lines. Okay. So these will turn out to be the constant u lines. Okay. So I am not actually able to. So it's something. So if I look only at this very region, forget about this region, only look at this very region. So when you take, let's say, r equal to rs, so it will look like this. It's simply a kind of cylinder. So these are actually, so this is something r equal to rs. So the way the geometrization of the bending of the space time. But if you take the other region as well, so it will look like something. So we simply call it as actually the Einstein-Rosen equation at the bottom, kind of. So these are all these things. I mean, this is at. These are the constant. Rs. Okay, so these circles are actually rs values. You can think these are once it reaches to where r equal to rs. So it falls to the singularity. So you can think. If you take only one part up, then you can think, let's say, the singularity is around here. So if you take both the parts, that means they are connected in this way. Okay? So we call this bridge as the Einstein-Rosen bridge, or it is used in fiction, it's known as wormhole. That's all. Thank you for being with me for this wonderful course. Okay? Okay? So, if you have any problem, so she asked for the notes. Okay, so I will be providing notes of GR today. Okay, but please return by evening. Clear? So I will be providing the notes for GR as well as the QFT, but return all these notes because you will not be coming from Monday. Notes here. So main notes